Okay, so in the last class we were talking about the measurement of pressure. So in the measurement of pressure, for first in atmospheric pressure, we use barometer. So to measure that atmospheric pressure, we generally use one instrument that is known as barometer. And the principle of barometer is very simple. So if we have this container filled with this mercury, and then this is mercury, and then when we just we use one cylindrical tube, and this is that cylindrical tube and filled with that mercury, and when just it turn by keeping its mouth down to this filled mercury, then this is now the new position of mercury up to this point, and this is vacuum created, and the height of this is calculated as h, and this h, this actually indicates the atmospheric pressure. So here in this point, the pressure is equivalent to atmospheric pressure. Here this pressure is equivalent to atmospheric pressure, and here this pressure is equivalent to 0 because there is vacuum. So the pressure difference between these two, this is equivalent to this height of this mercury column, and this pressure difference. So the pressure difference we have calculated. Pressure difference. Let's say if this point is A, this point is B. So in between A and B, it is equivalent to atmospheric pressure, and which is equivalent to rho multiplied by G multiplied by H. So in the last class we have discussed the pressure between these 2 points, and here this rho, this is that density of mercury, G, this is acceleration due to gravity, and H is the height of this mercury column. So by using this formula, one can calculate this atmospheric pressure by using this barometer, and we have calculated this is equal to 1.01315 into 10 to the power 5 Pascal. So this is that unit of this atmospheric pressure. So one atmospheric pressure is equivalent to, that is 1 into 10 to the power 5 Pascal. We have calculated by using this density of mercury, G, and this H. H is 76 centimeter. Here H is just a standard value, that is H is 76 centimeter. So now the second, if you want to calculate the pressure of gas, so in order to measure this pressure of gas, we use one instrument that is known as similar to this barometer. There is one manometer. So the structure of this this is that gas chamber, and here this is that tube, and in this chamber gas is filled with a constant pressure. So this is gas, and here one knob is used to block that. So this is that valve. When we open, gas will start flowing, and then we have this one U-tube surge system, and filled with mercury. So this is H. So simple structure is this. This is the opening. This is known as manometer. Okay. So the mechanism is very simple. When we open this valve, gas will start flowing, and because of the effect of this gas, the level of this mercury that will just shift it downward in this side of this U-tube, and similarly with the same amount, the height of this mercury column, this will increase in the second end. So the new level of that mercury, that will be here and that the increase in this column, because the shape is same, so this increase in this column is up to this. So in this point actually, let's say it is, let us represent this PA. This is actually the pressure of gas, because we are just blowing air through this. So this point, this is the pressure of gas, and this pressure of gas, it is measured by in here in this point. Since this is open, so here the pressure is equivalent to atmospheric pressure, because this is open system, open to atmosphere. So here this pressure is atmospheric pressure, and this gas point, let's say this is the second point here, and this is B. So that PA, it is equivalent to PB. This point is B. So this is actually equivalent to P gas. ये गैस के प्रेशर के बराबर होगा. And in this case, this PB is equal to atmospheric pressure is P atmospheric. So this is P atmospheric plus this the pressure due to this mercury column. So this is pressure due to the Hg column. And similar to this, we can calculate this is equivalent to, this is P atmosphere plus this is rho G multiplied by H. So this is P. Okay. So the difference between this P, this is PA. One can write this PB or PA. This is PA. So there is a difference between this P and PB minus P atmosphere. It is represented as P gas. One term is used. P gas, gas pressure. So this P gas pressure is the difference between these two. So PB minus P, and this P gas is ultimately P gas. It is equivalent to rho GH. So this is known as the gas pressure. Okay. So in ideal condition, mercury is used, but in place of mercury is partially in place of mercury, any incompressible liquid can be also used. So in standard manometer, mercury is used, but generally, if anyone wants to calculate the pressure of gas filled in any container, then a simple liquid which is incompressible, which cannot be compressed easily, that compressibility is very negligible, then it can be also used. Okay. So this is that measurement of gas pressure. Now, the variation of pressure at different point of liquid. So let us have variation of pressure in different kind of liquid column. So let us have, this is one container filled with liquid, and there is one cylindrical object in this container, and we can calculate that pressure here. This is point A, and also this pressure here, and if this height is h, and we can check that cross section area or the radius of this cylinder. So here this is the pressure. So the pressure difference between A and B. So this is PA is equal to applying force, let's say that is F1 multiplied by the area of cross section, upon pressure is defined as this area of cross section A, and PB, it is equivalent to, let's say here this force is applied, that is F2, here this is F1, so this is F2 upon, since area of cross section is same, cylindrical bar is here, so the area of cross section is same, and here F2, this is equal to F1 plus the force due to the weight of this cylinder. So this is F1 plus force due to weight of cylinder, and the weight of cylinder is just mg. So this is equivalent to F1 plus mg. So one can calculate this pressure difference PB minus PA. It is equal to this F2 by A minus F1 by A. F2 is this. So this is equal to F1 plus mg by A minus F1 by A. F1 by A can be cancelled. So this is equal to that mg by A. And m can be converted into in terms of density and volume. So this is equivalent to rho multiplied by the volume, that is A multiplied by Hg by A. Area can be cancelled. So this is rho Hg. So this pressure difference between PB minus PA, this depends on height. Okay, here this rho, this is the density of this cylindrical bar inside this liquid. Okay, if we remove this bar, there is no bar at all, and if this is vacuum channel just filled with water like this or that any liquid, and we want to calculate this pressure difference between this A and B point, and this height is h, then in this case also that PA minus PB minus PA, obviously inside this liquid the pressure will be more. So PB minus PA, that is equivalent to rho GH with the same formula. But here this rho, this is the density of this cylindrical bar, and here this rho, this is the density of this liquid. Building this. If this cylinder is in the horizontal direction, is it okay? So if this cylinder is in the horizontal direction, this is that container, the cylindrical bar is like this, and obviously that pressure difference of these 2 points, this depends on this diameter of this cylinder. But if we want to calculate this pressure somewhere here, this is PA and this is PB, then this PA minus PB, this is actually equal to 0. There is no pressure difference in the same level of that liquid inside any liquid color. Okay, so this PA, because that force applied here and force applied here, that will be identical, and the obvious cross section area is identical. So that's why this PA minus P and PB both will be identical, and the difference of this, that is equal to 0. Okay, so here this PA PB, that will be different, and this depends on the density of this cylinder, and here that obviously there will be a difference in the pressure, but this is only the factor of density of this liquid. The next is Pascal's law. We are using Pascal as a unit of pressure, and that is due to the work done by the novel work of Pascal. So now we will discuss that Pascal's So there is some thought experiments in order to understand this Pascal's law. And if we have this special setup filled with liquid, and this is that liquid column. this is that initial the point A. So initially there is no pressure applied here. We are not applying any pressure. Pressure applied here. This is 0. Then this is that the column is identical in these different sets of tubes connected with this. So this one is open. Atmospheric pressure is identical. So all these are open system. So the level of this liquid, that is identical when there is no pressure applied. Condition number first. But when we apply a constant pressure, then when this pressure P is applied here, constant pressure, and this is the piston, then the new position of this piston, it is somewhere here. This is the new position of piston. Means we are just we are applying pressure, and this is the new position of piston. And liquid is compressing, or liquid is shifting towards this. Then obviously level will increase, and irrespective of the diameter of this tube or the size of this tube, the level of this liquid, this is raised up to a identical height. So the next level will be this is that B, this is B, and this is B. Again, the height of this rising of this liquid level in these tubes, that will be identical. And why? Because we are applying pressure here, and this pressure is applied in each and every molecules of this liquid with the same amount. Okay, irrespective of the size of these tubes. Get my point? जैसे हम यहाँ पे प्रेशर अगर कोई लगा रहे हैं, तो ये प्रेशर जो है, ये लिक्विड के जितने भी मॉलिक्यूल्स हैं, जितने भी साइड ये हैं, सारे लिक्विड पे, सारे मॉलिक्यूल्स पे आइडेंटिकली अप्लाई होता है. इसलिए दिस इज दैट इनिशियल लेवल विच वन इज आइडेंटिकल. जितना प्रेशर यहाँ पे अप्लाई हो रहा है, उतना ही प्रेशर यहाँ पे अप्लाई होगा, उतना ही प्रेशर यहाँ पे अप्लाई होगा. एंड अकॉर्डिंगली द टोटल सम, ये जो लिक्विड का जो शिफ्टिंग होगा वो आइडेंटिकल होगा. ऐसा नहीं होगा कि इसका डायमीटर ज़्यादा है तो यहाँ पे शिफ्टिंग कम हो, इसका डायमीटर कम है तो इसमें शिफ्टिंग ज़्यादा हो. This observation is observed by this Pascal. Second, third experiment we have. This is the first one. Second, if this is that liquid container, and this is that liquid container, and we are just applying force pressure here, and this is point A, and this is point B. If this pressure P is applying here, so this pressure is identical here. If this liquid, one condition is this liquid is incompressible, density is identical. Okay, so whatever pressure we are applying here, that increase in the pressure, obviously there will be the pressure difference. Here we can PA and PB, we have just to differentiate this pressure as the air column, that H. So this PB is equal to PF plus rho GH. This is that true. Here the pressure will be different. But when we apply external pressure, and the same amount will increase in this rate, and the pressure difference will be identical. Whatever pressure difference we are creating here, that will be created additionally to this point P also. So according to Pascal's law, when a pressure is applied to any point of any incompressible, one term, compressible liquid. So liquid must be incompressible. Then the same pressure is transferred transfer to all points in the liquid. Same amount of pressure, you can say. Same amount of pressure is transferred to all points in the liquid. This is Pascal's law. Okay, so one hydraulic gas, it is a very wonderful discovery in because of this Pascal's law. By using one small pressure, very heavy objects can be lifted at a specific height. That is just because of this Pascal. So let us discuss. Is it okay? So according to this Pascal's law, when we apply any pressure to any point of the liquid, that liquid is incompressible. Then that pressure is transferred to each and every point with the same amount. So this is Pascal's law. So this is simple hydraulic gas. This is the wall. Filled with liquid. And this is that piston. One pressure is applied here. This is P1. Force is applied here. Pressure is here. And this area is A1. And this area is A2. And there is this can slide freely. And one vehicle. So according to Pascal's law, whatever pressure we are applying here, when we open this wall, whatever pressure we are applying here, these will be transferred to each and every point of liquid. This is the Pascal. So here, this pressure P is identical to this pressure P here, and this, let's say this is F1, A1, and this is F2. So here we are applying F1, and that F2 will be applied to in the opposite direction. So this F1 by A1, this is equivalent to F2 by A2, because pressure is identical in both points. Okay, since so this F2, it is equal to this F1 A1 by A2. So this is F1 by A1 multiplied by A2. Since A2 is much greater than A1, this area of this plate, and the area of this A2, this plate is much more big area covered. So this A2 is much greater than A1, so that F2 resultant force, that F2, it will be greater than F1. So by applying very small force here, we can get the output F2 with a higher value because of this Pascal's law. Even we can calculate that work done. If the shifting here, we are just applying force, this shifting is, let's say, this x1, and that shifting is x2 in this direction. Then separately you can calculate that this is the force. So that work done here at W1, it is equivalent to F1 multiplied by x1, and F2, W2, work done in this section. So let us have this is A, this is B. So work done and A, it is W1, and work done at point B or side B, that is equivalent to W2. So W2, that is equivalent to F2 multiplied by X2. So you can calculate this work done, F1 multiplied by X1, pressure is identical. So this W1 is equivalent to F1 multiplied by X1 and W2 is equivalent to F2 multiplied by X2, and this F2 that is equivalent to F1 by A1 multiplied by A2. Just put the value and you can compare, and both are identical and you can prove. Okay, can you? Let me put. So this is F1 by A1 multiplied by A2 and multiplied by X2. So liquid is incompressible. So whatever volume shifting in this direction, in this column, in left column, whatever volume shifting in this column, that is equivalent to the shift in the liquid in this column. Columns are different. So volume shifted in column A and is equal to total volume shifted in column B. So in this column, how much volume is shifted? This is identical to the volume shifted in this column. So this is equal to now A1 X1, the conversion area is A1, X1 is that just shifting, it is equivalent to A2 multiplied by X2. Okay, so this A2 X2 here can be substituted by A1 X1. So this is F1 by A1 multiplied by A1 multiplied by X1 because of this. So this A1 we can cancel. So this is F1 X1. So this is F1 X1. So the work done, whatever work we are performing here, work done is identical, but shifting is more because of effort is less. Work done is identical. Whatever work we are doing here, it is transferred completely to this. But the effort is less because of this Pascal. Get the point? What we have performed? So this work is F1 X1. Here this work done is this is F2 multiplied by X2. They are putting this F2 from this. And what's about this A2 X2? Because volume shifting in this column is identical to volume rising in this column. Whatever that volume compressing in this direction, this is rising in this direction. So this is A1 X1 is equivalent to A2 X2. When we just substitute A2 X2 is equivalent to A1 X2 here. So this work done, this is identical. So this is all about Pascal's law. Thank you.